Welcome! Today, we'll be exploring an interesting problem from LeetCode, problem number 566, Reshape the matrix. This problem challenges us to transform a 2D matrix into a new shape with given dimensions, while maintaining the order of elements. Let's dive in and uncover the solution together. In this problem, we are tasked with reshaping a given matrix into a new matrix with specified dimensions. The input matrix, represented as a 2D array called mat, will need to be transformed such that it has A rows and C columns. The reshaped matrix must maintain the same row-wise traversal order of elements as the original matrix, meaning the elements are read row by row from left to right and then placed into the new matrix in that same order. However, there is a key condition: if reshaping is not possible, specifically, if the total number of elements in the original matrix does not match the product of R and C, we simply return the original matrix without making any changes. The input format includes the matrix mat, which has dimensions mxn, and the integers R and C, which represent the desired dimensions of the reshaped matrix. The output will either be the reshaped matrix or the original matrix if reshaping is invalid. To help clarify the problem, let's look at an example. Suppose the input matrix is 1, 2, 3, 4, and the desired dimensions are R equals 1 and C equals 4. The output would be 1, 2, 3, 4. Here's why: the original matrix has 2 rows and 2 columns, and when we flatten it row-wise, we get a 1D array 1, 2, 3, 4. By reshaping this into a matrix with 1 row and 4 columns, the result is 1, 2, 3, 4. Now consider another case with the same input matrix 1, 2, 3, 4, but this time R equals 2 and C equals 4. In this scenario, reshaping is not possible because the total number of elements in the original matrix is 4, which does not match the required number of elements for a 2x4 matrix, which would be 8. As a result, the output in this case is simply the original matrix 1, 2, 3, 4. Here's another example to illustrate reshaping when the dimensions are compatible. If the input matrix is 1, 2, 3, 4, 5, 6, and the desired dimensions are R equals 2 and C equals 3, the reshaping operation is valid. The original matrix has 3 rows and 2 columns, and when flattened row-wise, it gives 1, 2, 3, 4, 5, 6. Rearranging these elements into a matrix with 2 rows and 3 columns results in 1, 2, 3, 4, 5, 6. Because the total number of elements, which is 6, matches the product of R and C, the operation is successful, and the reshaped matrix is returned. To summarize, the problem requires us to handle a few important constraints and edge cases. First, the number of rows m and columns n in the input matrix are always at least 1 and at most 100, while the desired dimensions R and C can go up to 300. The values within the matrix range from -1000 to 1000. A key edge case is when the reshaping dimensions R and C do not match the total number of elements in the original matrix. In such cases, we must return the original matrix unchanged. Another scenario to consider is if the desired dimensions are the same as the original dimensions, in which case the reshaped matrix will simply be identical to the input. Additionally, we must preserve row-wise traversal order regardless of the matrix's original or desired shape. These constraints ensure that the reshaping operation is both robust and efficient, even for edge cases such as very small or already 1D matrices. To begin, let's explore the brute force approach to reshaping the matrix. The main idea here is to directly map elements from the original matrix to the new reshaped matrix in sequential order. First, we flatten the original matrix into a one-dimensional array, which makes it easier to handle. Then, we use modular arithmetic to determine the position of each element in the new matrix. Specifically, for an element at index I in the flattened array, the row in the reshaped matrix is calculated as I//C, and the column is I%C, where C is the number of columns in the reshaped matrix. This approach has the advantage of being straightforward and avoiding nested loops, but it comes with a major drawback: it doesn't check if the reshaping is feasible. For example, if the total number of elements doesn't match the desired dimensions, this method will still attempt to reshape, potentially leading to errors. In terms of complexity, this method runs in O(n*(m) time and uses O(n*(m) space due to the intermediate flattened array. Now, let's move to a more optimized strategy that starts with validating whether reshaping is even possible. The reshaping process is only valid if the total number of elements in the original matrix matches the number required in the reshaped matrix. This can be expressed as our *c equals original underscore rows asterisk original underscore cols. If this condition isn't met, we simply return the original matrix unchanged. Once the dimensions are validated, we use a sequential traversal method to directly copy elements from the original matrix to the reshaped matrix without flattening. To map the elements, we can either use modular arithmetic or row major traversal logic. This approach is not only efficient but also avoids the additional space overhead of creating a flattened array. While the implementation is slightly more intricate than the brute force approach, it's both time efficient at n*m and space efficient, requiring 1 additional space, excluding the output matrix. An alternative approach leverages Python's built-in tools, specifically the itertools.chain function. The intuition here is to use itertools.chain to flatten the original matrix directly into a one-dimensional iterable, which is then grouped back into rows of the desired size using simple list slicing. This method is concise and takes advantage of Python's rich standard library to simplify some of the operations. However, it comes with its own trade-offs. While this approach is highly Pythonic and elegant, it may feel less intuitive for beginners and involves some overhead due to the use of external library functions. In terms of performance, it still operates in n*m time and uses n*m space for the intermediate flattened structure. The strategy we've chosen to focus on is the optimized sequential traversal method, as it offers the best balance between simplicity and efficiency. The key idea is to ensure correctness by first validating that the reshaping dimensions are feasible, which is done by checking if our *c equals the total number of elements in the original matrix. Once validated, the sequential traversal allows us to map elements directly without the need to first flatten the matrix, which saves both space and processing time. This method is efficient, with a linear time complexity of n*m, and it requires no additional space beyond the output matrix. Furthermore, it's robust, gracefully handling edge cases like mismatched dimensions. While it does require slightly more implementation effort compared to the brute force approach, the benefits of efficiency and robustness make it the ideal choice. Additionally, it avoids reliance on external libraries, making it more accessible for a wider range of developers. Finally, let's summarize the complexity of the chosen approach. The time complexity is n*m, where n and m are the dimensions of the original matrix. This is because each element is visited exactly once during the traversal. The space complexity is 1 additional space, as no intermediate structures are used other than the output matrix itself. This makes the method highly efficient for practical use cases while ensuring that resources are utilized optimally. The problem asks us to reshape a given 2D matrix into a new matrix with specified dimensions, our rows and C-columns. However, for the reshaping to be valid, the total number of elements in the input matrix must match the total number of elements in the reshaped matrix. To determine this, we first calculate the total number of elements in the input matrix as m*n, where m is the number of rows and n is the number of columns. Similarly, we calculate the total number of elements required for the reshaped matrix as our *c. If these two values are not equal, it means reshaping is not feasible, and in that case, we simply return the original matrix. Once we confirm that reshaping is possible, the next step is to flatten the input matrix into a single-dimensional list. By iterating through the input matrix row by row and appending each element to a new list called flat_list, we create a linear representation of all the elements. For example, if the input matrix is 1, 2, 3, 4, the flattened output will be 1, 2, 3, 4. After flattening the input matrix, the next step is to construct the reshaped matrix. We start by initializing an empty 2D list called reshaped_matrix, which will store the output matrix. To populate it, we iterate through flat_list in chunks of size C, where C is the number of columns in the reshaped matrix. For each chunk, we extract a slice of flat_list containing C elements, which becomes a new row in the reshaped matrix. These slices are then appended to reshaped_matrix one by one. For instance, if flat_list is 1, 2, 3, 4, and we want the reshaped matrix to have C equals 2 columns, the slices will be 1, 2, and 3, 4. Combining these slices, the reshaped matrix becomes 1, 2, 3, 4. Finally, we return reshaped underscore matrix as the result, which completes the algorithm. There are several key insights to highlight about this algorithm. First, flattening the matrix by traversing it row by row ensures that the elements are stored in a linear order consistent with the original layout. This simplifies the manipulation of data for reshaping. Second, mapping the flattened list into the reshaped matrix is achieved via slicing, which eliminates the need for complex indexing or calculations. Third, the validation step, where we check if m*n equals or *c, ensures that no data is lost or duplicated during the transformation. Finally, the algorithm is designed to handle edge cases predictably. For instance, if reshaping is not feasible, returning the original matrix ensures the input is preserved. In terms of data structures, we use the input matrix, a 1D flattened list to temporarily store all elements, and the final 2D reshaped matrix to store the output. To analyze the complexity of this algorithm, consider the computational and space requirements. The time complexity involves two main operations, flattening the matrix and constructing the reshaped matrix. Flattening requires traversing all m*n elements in the input matrix, which is an O(m*n) operation. Similarly, constructing the reshaped matrix involves iterating through the same number of elements, making this step also O(m*n). Thus, the overall time complexity is O(m*n). For space complexity, we need additional storage for the flattened list, which requires O(m*n) space, and the reshaped matrix, which also requires O(r*c) space. Since m*n equals r*c in a valid reshaping operation, the total space complexity is O(m*n). This ensures the algorithm is efficient in both time and space. To see the algorithm in action, let's walk through an example. Suppose the input matrix is 1, 2, 3, 4, and we want to reshape it into 1 row and 4 columns, meaning R equals 1 and C equals 4. First, we validate whether reshaping is feasible. The total elements in the input matrix are 2*2 equals 4, and the total elements required for the reshaped matrix are 1*4 equals 4. Since these values match, reshaping is possible. Next, we flatten the matrix, resulting in the list 1, 2, 3, 4. Then, we construct the reshaped matrix by slicing flat_list into a single chunk of size 4, producing the row 1, 2, 3, 4. Finally, we return the reshaped matrix 1, 2, 3, 4 as the output. Now let's consider an edge case where reshaping is not feasible. If the input matrix is still 1, 2, 3, 4, but the desired dimensions are R equals 3 and C equals 2, the reshape operation cannot be performed. This is because the total elements available in the input matrix are 2*2 equals 4, while the total elements required for the reshaped matrix are 3*2 equals 6. Since 4 is not equal to 6, reshaping is not possible. In this scenario, the algorithm simply returns the original matrix, 1, 2, 3, 4, without any modifications. This ensures that the algorithm handles invalid reshaping requests gracefully and predictably. This Python implementation solves LeetCode problem 566, Reshape the matrix. The goal is to reshape a given 2D matrix into a new matrix with specified dimensions, if possible. The function begins by extracting the dimensions of the original matrix, m rows, and n columns. Using these values, it calculates the total number of elements in the matrix. Reshaping is only feasible if the total number of elements matches the product of the desired dimensions R rows and C columns. If the dimensions don't align, the function simply returns the original matrix. If reshaping is possible, the code first flattens the original 2D matrix into a one-dimensional list using a nested list comprehension. This makes it easy to rearrange the elements into the desired shape. The reshaped matrix is then constructed row by row in a loop. For each row in the reshaped matrix, the appropriate slice of the flattened list is appended. The slicing ensures that each new row contains exactly C elements. Finally, the reshaped matrix is returned. This implementation is efficient, with a time complexity of O(m*n), where m*n is the total number of elements in the matrix, as every element is visited once during flattening and slicing operations. Edge cases are handled gracefully. If reshaping isn't possible, the original matrix is returned unchanged. This ensures the function adheres to the problem constraints and avoids unnecessary computations for invalid inputs. Here, we start by importing the necessary packages and defining our solution class. The core method here is matrix reshape, which takes three parameters: the original matrix mat, the number of rows R, and the number of columns C for the new matrix. First, we determine the dimensions of the input matrix by accessing its length and the length of its first row, storing these values in M and N. Next, we check if reshaping is feasible by comparing the total number of elements in the original matrix, M*N, with the total number of elements required for the new dimensions, R*C. If the two values do not match, it means reshaping is not possible, so we simply return the original matrix. Now, if reshaping is possible, we proceed to flatten the original matrix into a one-dimensional array called flattened. Using nested loops, we iterate over each row and then each element within the row, adding each element to the flattened array sequentially. This prepares us to reorganize the data into the new shape. After flattening the original matrix, we initialize a new 2D array called Reshape to hold the final matrix with the desired dimensions or by C. We then use a nested loop to populate this new matrix row by row. The outer loop iterates over the rows of the reshaped matrix, while the inner loop iterates over the columns. For each position, I, j, in the reshaped matrix, we assign the next value from the flattened array, incrementing the index after each assignment. Finally, once the reshaped matrix is fully populated, we return it as the output of the method. This implementation ensures that the data is transformed efficiently while maintaining the order of elements from the original matrix. To solve this problem, we start by analyzing the given input. The original matrix is a 2x2 matrix with the values 1, 2, 3, 4. Our goal is to reshape this into a 1x4 matrix, which means we want 1 row and 4 columns in the resulting matrix. First, we determine the dimensions of the original matrix. It has 2 rows and 2 columns, so M equals 2 and N equals 2. Next, we check if reshaping is even possible by comparing the total number of elements in the original matrix with the total number of elements required in the target matrix. For the original matrix, the total number of elements is M*N is equal to 2 times 2 equals 4. For the reshaped matrix, the required number of elements is R*C is equal to 1 times 4 equals 4. Since both totals match, reshaping is possible, and we can proceed with the next steps of the solution. After confirming that reshaping is possible, the next step is to flatten the original matrix into a one-dimensional list. This can be done efficiently using list comprehension. For each row in the original matrix, we extract the individual numbers and combine them into a single list. The flattened result is 1, 2, 3, 4. With this flattened list, we can now construct the reshaped matrix. Since the target matrix has 1 row and 4 columns, we take the first 4 elements from the flattened list. Specifically, for the first and only row, we take elements from index 0 to 4, resulting in 1, 2, 3, 4. The final reshaped matrix is 1, 2, 3, 4, which matches the desired 1x4 structure. In this example, we are given a 2x3 matrix, 1, 2, 3, 4, 5, 6, and our task is to reshape it into a 3x2 matrix with 3 rows and 2 columns. First, we determine the dimensions of the original matrix. It has 2 rows and 3 columns, so M equals 2 and N equals 3. Next, we check if the reshaping is valid. The total number of elements in the original matrix is M*N is equal to 2 times 3 equals 6. For the reshaped matrix, the required total is R*C is equal to 3 times 2 equals 6. Since the totals match, reshaping is possible. The next step is to flatten the original matrix. Using list comprehension, we extract all the values row by row to create the flattened list, 1, 2, 3, 4, 5, 6. This flattened list will be used to construct the reshaped matrix. Now that we have the flattened list, 1, 2, 3, 4, 5, 6, we can build the reshaped matrix row by row. The target matrix needs 3 rows, each with 2 elements. For the first row, we take the first 2 elements from the flattened list, which are 1, 2. For the second row, we take the next 2 elements, 3, 4. Finally, for the third row, we take the last two elements, 5, 6. Combining these rows, the reshaped matrix becomes 1, 2, 3, 4, 5, 6. This matches the desired 3 by 2 structure. The final output of this example is the reshaped matrix 1, 2, 3, 4, 5, 6. In this example, the input matrix is 1, 2, 3, 4, and the target dimensions are 3 rows and 2 columns. The first step is to determine the dimensions of the original matrix, which has 2 rows and 2 columns. Therefore, m equals 2 and n equals 2. Next, we calculate the total number of elements in the original matrix, which is m*n is equal to 2 times 2 equals 4. For the reshaped matrix, the total number of required elements is r*c is equal to 3 times 2 equals 6. Since the total number of elements in the original matrix does not match the total required for the reshaped matrix, reshaping is not possible. In this case, the problem specifies that we should return the original matrix as is. Therefore, the output is 1, 2, 3, 4. When analyzing the time complexity of this solution, we can break it down into several key steps. First, extracting the dimensions of the matrix involves simply calculating the number of rows and columns using the built-in len function. Since this only requires 2 direct length calculations, it takes constant time, or O1. Next, the reshaping condition, which checks whether the product of the matrix dimensions matches the product of the desired dimensions, is just a multiplication and comparison. This step also takes O1 time. The next major operation is flattening the input matrix. Using a nested list comprehension, we iterate over every element in the matrix. Since the matrix has m*n elements, this step requires O(m*n) time. Finally, constructing the reshaped matrix involves slicing the flattened list repeatedly to form rows. Each slice operation takes O(c) time, and since we perform this slicing r times, the total time for this step is r*c. Because r*c is equal to m*n, the slicing step also has a time complexity of O(m*n). Now, when we combine the time complexities of all the steps, the dominant cost comes from flattening the matrix and building the reshaped matrix, both of which take O(m*n) time. Thus, the overall time complexity of the solution is O(m*n). For space complexity, we start by noting that the input matrix itself is not duplicated, so it doesn't add extra space beyond what's already provided. Next, the flattened list, created during the flattening step, contains all m*n elements of the original matrix, which requires O(m*n) additional space. Similarly, the reshaped matrix, which is constructed as a list of lists, also takes up O(m*n) space because it stores the same total number of elements. When we sum these contributions, the total additional space used by the solution is O(m*n). Therefore, both the time and space complexity of this algorithm are O(m*n). To put this into perspective, if we were to use a more naive approach, such as employing nested loops to directly construct the reshaped matrix without creating a flattened list, the time complexity would remain O(m*n), because we would still need to iterate through all the elements in the input matrix. Similarly, the space complexity would also be O(m*n), as the reshaped matrix must still be stored in memory. The advantage of the current approach lies in its simplicity and clarity. By leveraging a flattened list, we streamline the process of reshaping the matrix, making the logic more straightforward and the slicing operations more efficient. Additionally, the use of Python's list comprehensions improves code readability without introducing any additional computational overhead. When we analyze the algorithm under different scenarios, the time complexity remains consistent at O(m*n). This is because regardless of the input or whether reshaping is feasible, the algorithm must process every element of the matrix. Similarly, the space complexity is always O(m*n), due to the need to store both the flattened list and the reshaped matrix, assuming reshaping is valid. This consistency across best, average, and worst cases demonstrates that the solution is optimal for the problem's requirements. Furthermore, any alternative approach with the same asymptotic time and space complexities would not offer significant advantages, making this solution both efficient and robust. When working with matrix reshaping, one common mistake is failing to properly validate the dimensions of the new matrix. Many assume that the reshaped dimensions will always divide evenly into the size of the original matrix. However, if the total number of elements in the original matrix doesn't match the required number in the reshaped matrix, the operation becomes invalid. This can lead to runtime errors or incomplete reshaping. Another frequent issue involves out-of-bounds errors during element mapping. Miscalculating the row and column indices when transferring elements can lead to incorrect placements or attempts to access invalid indices, breaking the logic of your code. Additionally, edge cases are often overlooked. Scenarios like empty matrices or reshaping to the same dimensions may not introduce new data but can still result in unnecessary computation or unhandled conditions, making the algorithm less robust. Another mistake to watch out for is unnecessary space usage. Some solutions create additional data structures to store intermediate results, which can significantly increase memory usage, particularly for large matrices. This deviates from optimal space complexity and should be avoided. Similarly, overcomplicating the mapping logic is a common pitfall. Using redundant calculations or deeply nested loops to manage index mappings can increase the time complexity of your solution. This results in inefficiencies that are easily avoidable by adopting cleaner and more direct approaches. Simplifying your logic while maintaining correctness is key to writing efficient code. In interviews, it's essential to focus on edge cases. For example, you might be asked to discuss how you would handle scenarios like reshaping an empty matrix, reshaping to a single row or column, or even reshaping a one-by-one matrix. Demonstrating a strong understanding of index mapping is also crucial. You should be able to explain how to convert 2D indices to 1D and vice versa, as this is a common pattern in matrix-related problems. Emphasizing solutions with optimal space complexity can set your approach apart. Avoid unnecessary auxiliary data structures wherever possible. Additionally, be prepared to discuss trade-offs between different approaches, such as brute force methods versus optimized solutions, and how those choices impact time and space complexity. Finally, clarity of thought is critical. Clearly explain how you validate the reshaped dimensions, such as by checking if the total number of elements matches before proceeding with the transformation. For alternative approaches, the brute force method is the simplest to implement. It involves directly iterating through the original matrix and filling the reshaped matrix. However, it often lacks validation and can use unnecessary space, which makes it less efficient. Its time and space complexity are both O(m*n). A more optimized approach focuses on direct mapping of indices, avoiding additional space usage. This requires careful calculations to ensure the correct placement of elements, but it achieves optimal space complexity with O(m*n) time and O(1) space. Lastly, in some scenarios, an in-place transformation might be possible. This approach minimizes memory usage but can significantly increase code complexity. Its feasibility depends on the constraints and size of the matrix, and its complexity varies accordingly. Choosing the right approach depends on the problem's specific requirements and constraints. Great job! In summary, we discussed the problem of reshaping matrices and the steps involved in approaching it systematically. Keep practicing similar problems, and remember to validate inputs and constraints carefully. Thanks for watching, and don't forget to like and subscribe for more helpful tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!